The last time we were together, we began Chapter 7, discussing electrons and their behavior. And before we discussed electrons, we began by discussing light. Light, we said, behaves very oddly. It can behave like a particle, which we call a photon, or it can behave like a wave, which we define in terms of its wavelength, the distance between two crests, or a full cycle's distance for a wave, the frequency, or how many wave cycles we could count passing by one point in a given second. Together, these manifest as the velocity or speed of a wave. Light waves travel with an upper limit for speed in a vacuum that we call the speed of light c, which has a value of 3 times 10 to the 8 meters per second. The relationship between these three quantities is that the frequency, nu, is equal to the speed of light, c, divided by the wavelength of light, lambda. We determined the frequency of orange light as 589 nanometers for sodium in street lamps last Friday. We calculated that this wavelength was equivalent to 5.09 times 10 to the 14 hertz when we applied this equation to the quantity 589 nanometers, or 5.89 times 10 to the minus 7 meters. For our new material today, what I would like to talk about is how we define light in terms of a particle as a photon. In relating these quantities of wavelength, frequency, or speed to photons, these particles of light, what we'll find is that all of our relationships are governed by energy, E. The energy of light is really the energy of a photon. And when we describe the energy of a photon, we'll describe how much punch a photon packs. The energy of a photon of light, E, is given as h times nu. In this equation, h is another fundamental physical constant of the universe. It is called Planck's constant. Planck's constant has a constant value, much like the speed of light did, and its value is 6.626 times 10 to the negative 34th power, with units of joules times seconds. These units again are joules J times seconds. The nu in this equation, Greek letter nu, is the frequency of light given in hertz or inverse seconds. Remember that hertz or inverse seconds, seconds to the minus 1 power, or 1 over seconds, are all equivalent to each other. The SI units for energy are joules, so energy will have units of joules, capital J. Let's use this equation to solve for the energy of the orange light, whose frequency we calculated on Friday to be 5.09 times 10 to the 14th hertz. We want the energy of orange light. If we had been given the wavelength and not the frequency, note that we would have had to calculate frequency anyway in order to use this equation up here. So, because we've already done that, we can start plugging in straight away to our equation from up top. The energy of a photon of light is Planck's constant. The constant value is 6.626 times 10 to the negative 34th power joules times seconds, multiplied by the frequency, 5.09 times 10 to the 14th power hertz, or inverse seconds, or 1 over seconds. In any case, units of seconds cancel out with units of hertz or inverse seconds. If we multiply through, taking care to enter these into our calculator with parentheses around scientific notation, and rounding to 3 significant digits at the end, we should result with 3.37 times 10 to the negative 19th power joules. This is our answer for our energy quantity. This is how much energy a photon with wavelength 589 nanometers packs. And what's more is that when we calculate energies for photons, we should expect to have really small values on the order of 10 to the minus 19 joules. If you ever calculate an energy and don't get something around 10 to the minus 19, then you'll probably need to check your calculations. Last time we were together, we briefly discussed this electromagnetic spectrum and left off by noting that the frequency of light, shown down here, and the wavelength of light, shown up here, trend in opposite directions. In other words, at the right-hand extreme of this electromagnetic spectrum, the radio frequency side, frequencies are very small and wavelengths are very big. As we move from right to left across the spectrum, frequencies increase and wavelengths decrease. What we can add today is that at this extreme, energy is highest. At the left-hand side, energy is high. Gamma rays are capable of breaking chemical bonds, whereas at the opposite extreme, on the right-hand side, energy is low. Radio frequency waves are pretty benign. As we move from right to left across this electromagnetic spectrum, our frequency goes up, our energy goes up, and our wavelength goes down. High frequency means high energy. High energy and high frequency means small wavelength. I would expect you to be able to compare two regions of this electromagnetic spectrum on the basis of frequency, energy, and/or wavelength to tell me that gamma rays, for instance, have larger frequencies, larger energies, and smaller wavelengths than, say, ultraviolet light. So you're likely wondering why we care about light if what we're after in this course is the discussion of electrons and their behavior. Well, it turns out that electrons themselves act like quantum particles. Einstein's photoelectric effect experiment demonstrated this. Electrons, like photons, can behave like waves and like particles at the same time. We say that electrons have discrete or quantized energy states. So, what does that mean? Like photons, electrons can only have certain energies. Their energies are governed by more complex equations than photon energies, so we won't calculate those in this course. But what we will say is that electron energies exist across a spectrum, and we can think about this spectrum as being sort of like books on a bookshelf. I'm going to draw out an imaginary bookshelf. We'll use just simple lines to represent shelves on a bookshelf. Perhaps here's one shelf, here's a second, a third, a fourth, a fifth, and a sixth. Now, I drew successive lines closer to each other than the previous set, not because I'm a bad artist, which I am, but rather because around an electron's distribution in the atom, successive bookshelves are closer together the higher we get. Remember that the universe is lazy, just like I'm lazy. I'm going to want the lowest bookshelf to be the most accessible, and I'm going to number bookshelves from there on up. The lowest bookshelf I'll call shelf number 1, and I'll number each successive shelf in turn in increasing order, from 2 to 3 to 4 to 5 to 6. Atoms will place electrons on shelves in the simplest way that they possibly can. Just like I'm lazy and will put an electron on the lowest possible shelf that I can, an atom will place an electron in the lowest possible bookshelf that it can possibly muster around its nucleus. Suppose that an atom has one electron to place on an energy bookshelf around it. It's going to want to place that electron on the lowest possible energy shelf, the one closest to the ground, like shelf number 1 here. Just like books cannot exist in the space between bookshelves, electrons cannot exist in the space between successive shelves around their nucleus. So an electron can sit on one shelf, but it can't ever occupy the space in between shelves. What electrons can do, however, is move from one shelf to another. This little electron here could be promoted to another shelf higher up if it's supplied with enough energy. We have to supply energy to move that electron, again, because our atoms are lazy and don't want to have to use any more energy than they absolutely must. So suppose that we shine some light on this electron, and light is governed by principles of both particle nature and wave nature. As a particle, it packs some energy. It turns out that light can transfer energy to an electron and make it move from one shelf to another. We can place our electron on a higher shelf if we can shine light with just the right frequency at that electron. We say that an electron absorbs light. It absorbs the energy of light and is able to move from one shelf to another. The caveat to this is that the energy supplied to our electron to allow it to jump from a lower energy shelf to a higher energy shelf around this electron bookshelf must be exactly equal to the spacing between bookshelves. Again, an electron can't just hover in midair between two shelves. If we tried to do that, it would just fall down to the shelf that's nearest. So, in order to get an electron to jump from one energy level to another, we have to supply just the right type of energy. If I had shown a different color light at this electron, perhaps I might have allowed it to move to a different energy shelf. Suppose that I shown blue light instead of yellow. According to our electromagnetic spectrum, blue light has more energy than yellow light. Perhaps blue light would have caused our electron to move to this energy shelf, the third one, rather than the second. Absorption is a process that requires just the right amount, not too much, not too little, but just the Goldilocks amount of energy supplied from light and absorbed by an electron to get it to move from one energy shelf to another along this bookshelf. Alright, so I just erased everything, and now what I've got is an electron that's sitting on the third energy shelf of its electron energy bookshelf, and we have removed any light source that had been supplying that electron with energy in the first place. So, all that electron has to support it being on the third energy shelf is energy from its atom's nucleus alone. Remember that our nucleus and our atom are lazy, so our atom isn't going to want to supply an electron with the energy needed to stay on that third bookshelf for very long. As soon as the light source is removed, that electron is going to jump back down to its ground state. We call the lowest energy level the ground state because it's the bottom floor of our electron energy bookshelf. And any states above that, any shelves that are higher than that ground level, are excited states. So right now, we'll say that our electron is in an excited state. As a result of the removal of a light source that was supplying this electron with energy, this electron isn't going to want to stay in its excited state for very long. It's going to want to immediately jump back down to its ground or lowest energy state. An electron can't just jump from one energy state to another, though, without supplying some sort of energy, as that would be in violation of the first law of thermodynamics. In order to go from one state to another, from this third shelf back down to the ground or first shelf in this example, an electron needs to shed some energy. To shed energy, an electron emits a photon. we call this process emission. A photon is a packet of energy. In an emission process, electrons shed or emit a photon, a packet of energy, in order to shed their excess and move back down to their ground state, their lowest energy state. So to recap, when an atom is exposed to just the right frequency of light, electrons around the nucleus can absorb and become excited by that light and jump up in energy level to a higher energy shelf. As soon as any light source is removed, we'll keep in mind that atoms are lazy and always want their electrons in the lowest energy level possible, the ground energy state. So electrons relax or emit a photon. When electrons fall to a lower energy level, they release photons of light. The wavelength of the photon that's emitted depends upon the size of the jump that electrons made. Just like an electron can't be placed between two energy shelves as it's moved up from a low shelf to a high one, an electron needs to shed energy in the form of a photon in an amount equal to the gap between its high energy level and its low one. The example on this slide shows the Balmer series of hydrogen, a very famous spectrum that demonstrates electrons jumping around energy bookshelves around a hydrogen atom. It was one of the first pieces of evidence that suggested that electrons must exist in these bookshelf-like energy states around atomic nuclei. Hydrogen has one electron, and if we supplied that electron with enough energy to move to the sixth energy bookshelf, eventually that electron could find its way down to the second on its way to the first energy shelf. As an electron jumps from the sixth energy shelf to the second, it sheds a photon of light with a large amount of energy, because this is a big energy gap. That large amount of energy corresponds to purple light. Alternatively, an electron from hydrogen that was excited to or supplied with enough energy to make it to the fifth energy shelf could, on its way back down to its ground state, make a stop at the second energy shelf. This energy gap is a little bit smaller than the previous one, and so not as much energy needs to be shed by an electron to get from the fifth energy shell to the second. The photon that's emitted by an electron through this process is blue. An electron that moves from the fourth energy shelf to the second emits a smaller energy photon still, with a color that's teal. And lastly, an electron that goes from the third to the second energy shelf emits a photon with a color that's red. The reason that I'm not showing you jumps for electrons all the way back down to their ground state is that this energy gap is really high. In order to emit a photon with enough energy to go all the way back down to a ground state, hydrogen's electrons need to emit very energetic photons, so energetic that they don't show up in the visible region of the electromagnetic spectrum. They are ultraviolet photons. This jumping around of electrons by either absorption of photons to go up in energy shelves or emission of photons to move down energy shelves suggests that our atom as a whole can behave very oddly. There are a few lingering questions that aren't addressed by just this bookshelf model alone. We would like to know why a nucleus doesn't just pull an electron into it and merge with the electron. Remember, our nucleus is comprised by protons with positive charge and neutrons with no charge at all. Overall, our nucleus is positively charged. Why doesn't it just pull electrons into it? And even though hydrogen is a simple case with one electron, what happens with atoms that have more electrons around their nucleus than just one? This was a problem that was addressed about a century ago in the 1920s. Early on in the 20th century, Niels Bohr began addressing these issues by constructing a new model of the atom. He suggested that electrons exist in circular orbits around a nucleus, sort of like planets exist in orbit around a star. As electrons change their orbital path, they emit or absorb energy, depending upon whether they get closer to the atomic nucleus or further away. Bohr was able to calculate the energy levels of those orbital paths, and for this, he received the Nobel Prize in Physics. This is a depiction of Bohr's model of the atom. For hydrogen, with just one proton and one electron around it, Bohr calculated these 6 energy orbital paths. Again, sort of like planets orbiting a star, except the star is the nucleus of an atom. As electrons change the orbital path that they're on, they can emit light of various colors and wavelengths. Visible light is always produced as hydrogen atom's electron moves from a high energy level to the second energy level. Ultraviolet light is produced as an electron moves to the first energy level. Infrared light might be produced as an electron moves to the third energy level. Overall, this was a very successful representation of the behavior and nature of electrons, as scientists in the early 20th century and late 19th century were able to measure. But it still had a few drawbacks and doesn't completely explain everything that we know now about the nature of the atom's electron cloud. In the mid-1920s, Werner Heisenberg showed that it's impossible for us to be able to calculate both where a particle as small as an electron is and how fast it's going. Where a particle is governed by the particle's position in space, and how fast it's moving is given by its momentum. The Heisenberg uncertainty principle tells us that we cannot know precisely both the position and the momentum of a quantum particle based on our inability to make a measurement with much certainty at the length scales at which electrons exist. Remember, electrons are exceedingly small, much smaller than a proton or a neutron, and as such, we have difficulties measuring their position. Our uncertainty in position contribute to uncertainty in momentum, and therefore we can never know both with 100% certainty. This idea of Heisenberg's seems to contradict Bohr's model of the atom, because Bohr's model suggests that we can know the orbital path that an electron is on. And if we know an orbital path, we can use some tricky physics to be able to figure out its angular velocity and therefore angular momentum. Mathematics would tell us with certainty both where an electron is and what its speed or momentum would be. If we accept Heisenberg's uncertainty principle as a course of nature, then Bohr's model of the atom cannot be sufficient to describe the real nature of electrons around an atom. It turns out that we'll need a new mathematical representation of electron distribution around an atom that was constructed in the 1920s. Modern quantum mechanics is predicated upon this idea that we can calculate not exactly where an electron is and exactly how fast it's going, but rather a probability about where an electron is likely to be found, its address, through use of Erwin Schrödinger's equations. Schrödinger's equations treat an electron like a wave. Much like we can treat light as both a wave and a particle, we can treat electrons like a wave and a particle simultaneously. Schrödinger's equations give rise to quantum numbers that describe the likelihood of finding electrons in certain places around an atom. The first quantum number that we'll discuss in class is the principal quantum number that we'll abbreviate N. N is very like the energy levels of an electron energy bookshelf. But instead of saying that an electron has to be on a shelf, we'll describe a shell or a cloud in which electrons are likely to be found. As this principal quantum number n increases, these shells or clouds move farther and farther on average away from the nucleus. The values for n can be 1, 2, 3, and so forth, all the way on up to infinity. The second quantum number that we'll discuss in class is the azimuthal quantum number, or more simply, the orbital angular momentum quantum number, which we'll abbreviate L. This quantum number will describe a shape of an electron orbital, sort of like a box on an electron energy bookshelf, in which we're likely to find an electron. Another analogy that might be helpful for you is that these quantum numbers will specify an address at which we're likely to find an electron, where a principal quantum number is sort of like the city in which you live. An azimuthal quantum number is sort of like the street you live on. Even though you might live on a street in a particular city, you're not always on your street. You might be going to school, you might be going to work. You're likely to be found on that street, but you're not always there. An electron is likely to be found in a particular orbital within a particular energy cloud. When we come back to class on Friday, we'll discuss what that means and start to assign principal quantum numbers and orbital angular momentum quantum numbers to electrons around an atom. For now, what we'll say is that these orbital angular momentum quantum numbers, L, can have values ranging from 0 to 1 to 2, all the way up to whatever energy shell number we're in, -1. The real important takeaway from this is that L values 0, 1, 2, and 3 are the only values that we currently recognize for electrons to have in a shell around an atom. These are so intricately tied to the history of this science that we use an alternative letter designation to describe these numbers. This is based upon historical evidence that wasn't well understood at the time it was discovered, for features of a spectrum of light emitted by electrons that were either sharp, principal, diffuse, or fine. SPDIF, SPDF. We'll use these letter designators to alternatively express these nebulous numbers. S means L is equal to 0, P means L is equal to 1, D means L is equal to 2, and F means L is equal to 3. On Friday, we'll explore this concept in class a little bit further and talk about the shapes of orbitals that electrons can occupy.